What's up, weebs? Today we are going to review all of Unit 5. Unit 5 was all about logs and exponentials. And I couldn't think of a clever word for exponential, so I just drew this ugly looking explosion. But you guys can't tell me it looks ugly. You guys have to gas me up. You have to be like, no, Barton, that's the coolest explosion I've ever seen. So, I'm very self-conscious about the way I draw. So you got to make sure you hype me up, otherwise it's never going to happen again. But either way, we are going to talk about logs and exponentials. We're going to talk about expanding them, condensing them, solving equations with them, some growth, some decay, interest, and graphs. So that's a whole bunch of stuff. But don't worry, this video will probably only be like an hour and a half long. So strap in, buckle your seatbelts, get your notes out, and let's go review. So before we can start talking about all the cool problems, we need to remember all of our different properties of logarithms. You're going to say, what about exponentials? Well, what about exponentials? They're pretty similar to logs, and they're kind of something I expect you to remember from algebra dos, but if not, maybe we'll sprinkle them in the video. So the first property of logarithms that you guys need to remember is the product property. And you know that I can't write and talk at the same time. So you're going to have to listen. Product. I wrote product. See, that's what I'm talking about. Whoops, forward. Property. There we go. I was too busy trying to look like I could write and talk at the same time that I messed myself up. So what the product property says for logarithms is if we have two logarithms, count them, 1, 2, and they have the same base and they are being added together, what you are allowed to do is condense these logarithms into a single logarithm with the same base that you started with, and you take their arguments, that's the fancy word for the stuff inside the log, and you multiply them together in the new log. Likewise, you can go backwards. So if you have a logarithm with some things being multiplied together inside of it, you can expand that log by giving each part of the argument its own logarithm and then adding those logarithms together. The next property that we are going to talk about is the quotient property. And I'm impressed that I spelled the word quotient correctly. Right in before I didn't spell it correctly, and you're all going to make fun of me. But this is basically the exact same thing. This is just for multiplying and adding. So it makes sense that we have one for subtracting and dividing as well. So if instead you are subtracting instead of adding, then you're going to divide instead of multiply. That's all the difference is. The important thing to note here is whichever logarithm has the negative term in front of it, its argument goes on the bottom of the fraction. So that's an easy way to tell where am I supposed to put this thing once I condense. Or if you're going the other direction, because you're allowed to, it's a good way to tell, is the logarithm supposed to be positive or negative? Stuff on the bottom always goes in a negative log. Stuff on the top goes in a positive log. And then the last property of logs that we need to know is the power property. And the power property just says that if we have a coefficient in front of our log, so it's like 3 times log of 6, that you are allowed to take your coefficient and turn it into an exponent on your argument. If you have multiple things in the argument, the exponent will go on the outside, and then you'll of course use your exponent property to distribute it. So likewise, if you have something inside a logarithm with an exponent you don't like, you can take that exponent and move it in front of the log and turn it into a coefficient. So let's look at a couple of examples. We're going to do one expanding and one condensing problem just so you get the flavor of both. And I picked 2 of the harder examples that I just have laying around so that you get kind of the full flavor of it. take a little sip of water there just to refresh my palate. So let's start with expanding. Actually, let's start with condensing. I changed my mind. Condensing, I think, is a little bit easier because we're going from the left side of all of these to the right side. So it seems like it flows a little better to me. So the first thing we're going to do for this condensing problem is all of these coefficients, we're going to turn them into exponents. So I'm going to rewrite this. Log base 5. Now this is going to be 2t to the power of 4 minus log base 5 of t squared to the third power minus log base 5, and we're just going to keep this the same because the coefficient's a 1, so t to the fifth power. All right, now we need to clean up these exponents a little. These exponents need to be distributed to the interior exponents. So this is going to turn into log base 5 of 2 to the fourth power t to the fourth power minus log base 5 of t to the sixth power, because we're multiplying our exponents, minus log base 5 of t to the fifth power. We'll clean up this coefficient probably in our next step. So what we want to do now, we don't have any more coefficients, but we have some logs being subtracted. So we're going to use our quotient property to condense them into a single log where the arguments are multiplying and dividing. So because this logarithm is positive, it doesn't have a sign, so it's an implied positive, its argument is going to go on the top. Because these two logs are negative, their arguments are going to go in the denominator, and we're going to multiply those arguments together. So when we condense, all of our logs are going to stay the same logarithm. So we're going to put our log base 5. This one was positive, so its arguments go on the top. I'm going to go ahead and do 2 to the fourth power now. So 2 times 2 is 4, times 2 again is 8, times 2 one more time is 16. Then we bring down our t to the fourth. Now these logs are both negative, so their arguments go on the bottom. T to the sixth, t to the fifth. Now our log is condensed, but we need to not be lazy about our simplification here. So we're going to simplify this business. So when we're multiplying two variables together, we add their exponents. So this will be t to the 11th. So we're going to have log base 5 of 16 t to the 4th over t to the 11th. And now because we're dividing, 4 of these t's cancel out with 4 of these t's. So all 4 of these go away. And then 11 minus 4 is 7. So this is log base 5 of 16 over t to the 7th power. And this thing looks maybe a little bit more friendly than this mess up here. All right. I'm going to erase this just in case I need to write big or, draw pretty pictures. So on this side, we're going to do some expanding. So the first thing that we're going to do is we're going to take this exponent and we're going to turn it into a coefficient using our power property. So this is going to become 3 log base 8 of the cube root of x over y squared. All right. Now, these exponents and stuff, we can't really just throw them out in front because they're two different ones. So what we're going to do is we're going to separate the numerator and the denominator of this by using our quotient property. So because we have a fraction and we're dividing, it's going to turn into subtraction. And remember, the bottom is always the one that gets the log with the negative on it. So we're still going to have this 3 log base 8. So 3 log base 8 of the cube root of x minus, because this is on the denominator, 3 log of y squared. log base 8 of y squared, excuse me. All right, now we can expand this and we can expand this. To expand this, we need to do some remembering how exponents work. If we have a root, we can rewrite that as an exponent. So remember, if you have, let's pretend it's this. If you have the cube root of x squared, you can rewrite this as a fraction exponent. So the thing inside, the radicand, is going to stay the same, so the x. The exponent is the numerator of your new exponent, and the root number is the denominator. So this would turn into x to the 2/3 power. Here, because we don't have an exponent, it's an invisible 1. So ours will be to the 1/3 power. So we have 3 log base 8 of x to the 1/3 power minus 3 log base 8 of y squared. We'll just copy it for consistency. Now we're going to take our exponents and turn them into coefficients. So we're going to throw them to the front and we're going to multiply them to the 3 that's already there. So 3 times 1/3, those cancel. So this one becomes simply log base 8 of x. And then 2 times 3 is 6. So this will be minus 6 log base 8 of y. And this is as expanded as we can make that. All right. Moving right along. Now we need to solve an equation using logarithms and exponents. In case we forgot, I've copied the steps here. So our first step is going to be isolate the exponential term. That means the base and its exponent. So in this equation, our base is 5 and its exponent is 3x plus 1. We don't want this minus 2 here, so we're going to isolate it by dividing both sides by -2. So these -2's cancel. We have 5, 3x plus 1 as the exponent equals a negative divided by a negative is a positive 31. Now we need to rewrite the equation as a logarithm. So let's talk about logarithms really quick. If we have an exponential, so it's got a base, it's got an exponent, and it equals some number. The way that is going to turn into an exponent, or rather a log, excuse me. The way this exponential turns into a log is it turns into log. The base of our logarithm, the little subscript number, is whatever the base of the exponential is. The inside of our logarithm is going to be the answer of the exponential. And then the log tells us what the exponent was. So the answer of the log is the exponent. So we're going to follow this same pattern to rewrite this as a logarithm. So our base is 5. So we're going to have log with a base of 5. The inside of our logarithm is whatever the problem is equal to, so 31. And it equals our exponent, 3x plus 1. All right. Now, this thing right here, your logarithm, this is not going to simplify nicely. So what you need to do is type that into a calculator. So I'm going to type into a calculator really quickly while you're not paying attention. And I'm going to tell it to give me a decimal. It doesn't want to give me a decimal. Yes, it does. Okay. So this is about 2.13366. And good enough. Just maybe 4 or 5 decimal places. The more decimals you use, the more accurate your answer is. How many are we supposed to use? Follow your heart, kid. Equals 3x plus 1. Now the rest is easy. We just solve for x. So we subtract 1 on both sides. Those cancel. So this is 1.13366 equals 3x. And then we use our calculator to divide both sides by 3. So subtract 1, divide by 3. X equals 0.377885. On your homework, it'll tell you what to round to. It's not going to want all 6 decimal places of this. It might say round to the hundredths place or something like that. So tens, hundredths, thousands. So we look at the, to round to the hundredths, we look one past it. This is above 5, so that means this number goes up. So if you round to the hundredths, it would be 0.38. I believe you might want to be careful. I think that if you write it as x equals 0.38, I think it counts that wrong. It usually doesn't like when you put a 0 in front of it, so just be aware of that. 0.38 and 0.38 are the same thing, but because of the way your homework's graded, I would try this one. All right, so there's solving logs. Not too bad. Okay, now this one is a little bit bad, and luckily I've got my handy dandy calculator sitting on the ready for this one. But exponential growth and decay. So it says cesium-137 has a half-life of 30 years. That means however much you start with, after 30 years, you're going to have half of that much. So if you buy a sample of 100 grams to celebrate graduation, how much will be left when you retire in 47 years? So what we need to do for this problem is we need to use our exponential growth equation. And what that equation is A equals P e to the kt. P is our starting amount, A is our ending amount, E is Euler's number. It's a button on your calculator. It's E equals 2.7, I want to say 81. It might be 1.8. I forget. Euler would be ashamed. He's my favorite mathematician. I feel like I should know this. K is our growth rate, or our exponential decay rate. It's how quickly or slowly things are decaying. But K is a number we have to go and calculate for ourselves before we can do the problem. And then T is our time. But this is the formula we want to use. So our first step is we have to go find K. So we're going to plug in our ending amount, our starting amount, and our time, and our Euler's number constant. And we're going to use what we just learned on this slide to solve for K. So let's go find those numbers first. Our starting amount, it says you buy a sample of 100 grams. So our starting amount is 100. Now it tells us the half-life is 30 years. This sounds like a time to me. So T equals 30. And what half-life means is after these 30 years, you will have half of what you started with. So if we start with 100, we're going to end with 50. So what we're doing here is we're going to plug these three numbers in to get K, and that kind of just like calibrates our equation so that we can plug in whatever numbers we want to get ending amounts for any time, right? Specifically that 47. But we kind of have to calibrate the equation first by getting that specific K value. So let's plug these in. So we have 50 equals 100 e to the k times 30. Now we're going to solve for k. So first we isolate the exponential by dividing by 100. These cancel, so we have 0.5, or a half, equals e, and I'm just going to put this in a little bit nicer to look at, 30k. Now we rewrite this as a logarithm. Because our base is e, we're using a special logarithm called the natural log. That just means log base e. This thing shows up often enough that they gave it its own special name called ln, or the natural log. The argument of our log is the answer to the exponential, so 0.5, and the logarithm tells us the exponent, so 30k. Now we have to type the natural log of 0.5 into our calculator. I believe there will be a button on your calculator that says ln, so just press that button and then put 0.5 in, and it'll tell you that it's negative 0.693147. Let's make our 3 look like a 3, equals 30k. And now we're going to divide both sides by 30 to get k by itself. So k equals negative 0.023105. All right, we need to save this. Put this thing somewhere you're not going to lose it. Get a tattoo of it. Maybe not. Actually, no. Don't get a tattoo of that. But you want to put it somewhere you're not going to lose it. So let's take this thing and we'll put it over here. Nah, we'll leave it where it was. Never mind. We'll put it back where it was. All right. So we have k. This is how we calibrate the equation so that it'll work. Now what we want to do is we're looking for the ending amount. How much is left? What's the ending amount after 47? So we still know what we started with. Now we know k, and they give us a new time. It's 47. So we're going to plug in p, k, and t, and then we're going to calculate a. So let's do that. A equals, our starting amount is 100. E to the power of k, so negative 0.023105, times our time, and the time we're actually interested in is 47 years. So we'll put in our 47, and k and t are being multiplied together. So now this whole thing, you can just go shove that entire thing into your calculator. So you'll type 100 times e to the power of negative 0.023105 times 47. Hit enter, and then it will spit out a number. So a equals, 33.7, we'll round, 6 grams, because our units are in grams right there. So after our long 47 year of science or math or whatever it is we do, our little rock is going to decay, and we're only going to have that much left. Sad. Oh well. Next problem. All right. For our interest problems, you have to be aware that there are two types of interest. There is what is called continuously compounded interest. Compounded interest. So this is kind of like stock markets or bacteria growing or things that are happening all the time. They never stop. Does it make sense to say, well, how many deer are there right now? It's kind of a fishy thing, right? It's like, well, all the deer don't wait till May and go, okay, now have the baby, right? They just have those baby deer whenever they want. The other thing, the other version of interest or exponential growth that we could talk about is incrementally compounded interest. Let's see, is there another word we could use for incremental? Not that I can think of. I'm a math teacher, sorry. My thesaurus knowledge is a bit lacking. But this is interest that kind of humans calculate at a regular interval. So when you go to the bank, it'll calculate your interest maybe every single month. You'll get the interest on your bank account, and they'll give you your like 13 cents or whatever it is based on what you have in your bank account. So this is for when the growth happens at a regular interval, every month, every week, twice a year. This is for things that grow continuously at an unregulated rate, like bacteria growing in a petri dish or things like that. So let's read our question. It says, you invest $5,000 in an account with an interest rate of 2% compounded quarterly. So if we were going to use this one, this word would say continuously instead of quarterly. So that's giving us a big hint. We need to use the incremental version, not the continuous version. And they want to know, how much money would you expect to have after holding the account for 10 years? So you're going to put your $5,000 in your bank account. You're not going to touch that thing for 10 years, and then you're going to come back and reap the rewards. So in this equation, starting amount, ending amount, interest rate as a hang on, forward eraser. I said decimal and I wrote a percent as a decimal. N is the number of times compounded. And then T is your time. N is in 2 spots though. Okay, there we go. So you invest $5,000. That's our starting amount. In an account with an interest rate of 2%, that's our rate. As a decimal, here, let's write these down, 5,000. As a decimal, 2%, we move the decimal 2 places left. So our rate is going to be 0.02. Compounded quarterly. For these compounding numbers, you want to ask yourself how many of these things occur in a year. So if we said daily, it would be 365. If we said monthly, it would be 12 because there are 12 in a year. Quarterly, you know the word quarter. It's 1/4. So there are 4 quarters in a year. So N equals 4. How much money would you expect to have after holding an account for 10 years? So T equals 10. We're looking for the A value. So we're going to plug these 4 numbers in and then just beat this thing to death with a calculator. So A equals 5,000 times 1. The plus and minus here is for growth and decay. The plus is growth. The minus is decay. Because we're gaining money, we're gaining the money off of the interest, we're going to use the plus. If we had something that said like you have a population of polar bears and due to climate change and the irresponsibility of humankind as a whole, 70% fossil fuel industries, but I digress. And the polar bears are dying, so they'd be decreasing, we'd use the minus. But because we're gaining money, we'll use the plus here. Rate is 0.02 over N, which is 4, to the power of N times T. Now this thing, you can just shove the whole thing into your calculator. I typically try and clean it up a little bit first so that I can type it in a little easier. So 1... let's go ahead and do 0.02 divided by 4. That's 0.05, so 1.05. And then 4 times 10 is 40. And then this is a little easier for me to type into a calculator. So we'll do 5,000 times 1.05 to the power of 40. Hit enter. And at the end, A equals, hold on. Sorry, there should be 2 zeros here. I almost gave us way too much money. Let me go ahead and fix that, put another 0 in. Okay, in the end, we're going to have $6,103.97. So we gain $1,100 just for not touching money. Just for being patient, they're going to give us $1,100. Sounds like a pretty good deal to me. All right. The last thing we need to talk about before I send you on your way are the graphs of logarithms and exponentials. So I've graphed 2 just parent functions here. This one is actually y equals the natural log of x, and this is y equals 2 to the power of x. Let's talk about the key features here that you want to know about, and then we will send you on your way. So logarithms have a vertical asymptote. Typically, they are right on the y-axis, but if you translate your graph left or right, so let's say you put a -1 here to move your graph to the right 1, that'll move your asymptote with it, right 1, and then there you go. The important point you want to be looking for here is this one right here. This point is at 1, 0. It will always be 1 to the right of your asymptote, and this y value comes from the k. If we shift this up some amount, plus k at the end, our vertical shift, this spot will shift with it. So this will be 1 to the right of your h value, and then this y value here is going to be whatever your k is. Cool. So vertical asymptote usually has a point at 1, 0, but if you move the whole graph right, left, up, down, this point will move with it. So you kind of want to try and find that one. For exponentials, because it's an inverse of this, the whole thing is reflected. So this actually has a horizontal asymptote starting on your x-axis. And that horizontal asymptote is determined by that plus k at the end. Because I don't have a plus k, y equals 2 to the power of x, it's not shifted up or down. This 1, 0 point on exponentials turns into 0, 1. So that will happen on any exponential, even if it's like 3 or 4 or whatever the base is. The base doesn't matter. All exponentials, as long as you don't shift them, have the 0, 1 point. The only difference between a base 2 and a base 3 is how sharply this curves. So that might be 3. It just grows a little quicker. And then you can, of course, take this graph and shift it left, right, up, down. You will see minus h in the exponent with your x, and then your k will be plus a number on the outside separate from the base and the exponential. All right. I hope this video helps. If it doesn't help, make sure you go give me a piece of your mind in the WebEx. You will have an assignment on this. I hope you enjoy it. Thanks for coming to my TED Talk.